All right. Another way that two events can interact is with what's called conditional probability. So when we looked at the intersection of events and the union of events, you could almost think of those two events as occurring at the same time. So two conditions that both had to be met or that were occurring at the same time. Conditional probability is you have two events, but they may not be occurring at the same time. One may occur ahead of another. And because one event occurs first, that may affect the second event, which occurs last. So that's what we're going to be talking about with conditional probability. So conditional probability is calculating the probability of two events such that the probability of A given that C occurs first. So it takes place when an event C affects the outcome of another event A that follows it. So kind of in this format, this vertical bar means given. And this event that we put last, this is actually the event that occurs first. And this one here ahead of the given symbol, this is the event that follows, okay, or occurs second. So consider event C already occurred, creating a new sample space to calculate the probability of A. So there's, a lot of different ways that doing conditional probability of two events can occur, and it really just kind of depends on how those two events were initially defined. So let's look at this first case here, where the two events A and C are disjoint. So meaning that there's no overlap. So if we're looking at A, given that C occurs first, if C occurs first, then we know that whatever occurs second has to be inside of event C. And you'll notice here that there's no part of A that is in C. So therefore, the order of that conditional probability is going to be 0. There's no overlap. So event C occurring first eliminated outcomes of A from ever occurring at all. All right, so I think this is probably still a little too abstract. So let's maybe move to this second example where event A and event C are not disjoint, okay, meaning they do overlap. So when we look at A, given that C occurs first, so the fact that C occurs first, what that ends up doing is that ends up changing the sample space to C. So that's kind of what I've got drawn here. The sample space changes. So because C occurs first, the sample space shrinks down to C. Okay, so forgive that shifting around. It's just something that Microsoft Word does. And now that the sample space has shrunk down to event C, then we're interested in A occurring, given that C occurs first. And so what's left of A is in the intersection with C. Okay. So what we've got is the order of A given that C occurs first is going to be the order of A intersect C. So the order of this intersection right here. Okay. And so when we calculate the probability of A given that C occurs first, that's going to be the order of A intersect C. And usually it's over the sample space, but now the sample space has shrunk to C. So it's going to be the order of A intersect C all over the order of C. And another way of representing this ratio is if you think of the probability of the intersection all over the probability of just event C. Those two are equivalent. So the fact that C occurred first did reduce the outcomes of A occurring. And so the sample space reduced to that of event C. And that's what I tried to represent by drawing these arrows going in from the border of the sample space down to event C. All right. Now, another example of, I would say, almost conditional probability where one event affects a second event from occurring is you see that when the sample space changes its order, okay, when the sample space changes itself. And so when one event occurs first, it reduces the size of the sample space from one number down to another. And you'll kind of see here in this example, I've got a sample space order of 52 and 51. And so the easiest example of this is when you've got a 52 card deck and you take one card and you keep it, then you're left with 51. So the sample space, the order of the sample space is changing from 52 to 51, given that you kept the first card. Okay, so that's kind of in the gray area of conditional probability. So conditional probability depends on two events intersecting. All right, so if, to calculate conditional probability, you want to make sure that two events intersect. If they don't intersect, then the conditional probability is just going to be 0. Okay, so that can be a shortcut if you're given a problem and you're trying to calculate the conditional probability. If there's no overlap between those two events, then the probability is just going to be 0. Okay, so let's look at an example here. We're looking at one six-sided die, the sample space of one six-sided die, and the probability of one event versus the conditional probability of two events. So this is actually kind of two examples put side by side, so you could kind of see the difference. So what we're given is a six-sided die roll, and the question is, what is the probability of rolling a 2 in two different examples or two different scenarios? So scenario 1 is the probability of one event, so the probability of just getting a 2. This is what we learned at the very beginning of this chapter. So here the sample space for a six-sided die is 1 through 6. Our event is rolling a 2. So here, this is our Venn diagram. And the order of event, E, is just going to be 1, because there's only one element in that event. And the order of the sample space is 6, okay, because that's how many possible outcomes that we have with a six-sided die. So the probability of a single event is the order of the event over the order of the sample space, which will be 1 over 6, which is 16.7%. So since we know nothing about the results, the probability is defined by the sample space of the experiment. So down here in the denominator, okay, this denominator, is kind of dominated by all possible outcomes. All right, so this is what we've already done. Okay, this should have been kind of a rehashing of what we've done before. Now, scenario 2 is a new example using conditional probability. So what's the conditional probability of two events? This will in turn give a reduction of the sample space to the second event. So what's the probability of getting a 2 given that we know that the outcome is going to be even? So now we've got two events. We have event E, which is 2, the outcome of a 2 occurring. And the second event is event F, where we know that the outcome will be an even result. So here's the Venn diagram, which kind of represents this probability here. So event E is the event of getting a 2. I apologize for that jumping around. I can't really help that. And event F is getting an even number. So here's event F, and that's going to be a 2, 4, or a 6. All right. So since we're looking at the probability of 2, given that an even result occurs first, our sample space is going to shrink down to that of event F. Okay. And so the probability of E given that F occurs first is this formula here. It's the probability of E intersect F over the probability of F. And we can write the probability of E intersect F as the order of E intersect F, and the probability of F we can write as the order of F. And so how many elements do we have in the intersection between those two? We have one element. So E intersect F only has 2 in it. So that's only 1. So that's where E intersect F equaling 1 comes from. And event F has 3 elements in it. Really don't like it jumping around like that. So the order of F is equal to 3, which gives us a fraction of 1/3, or 33.3%. So notice the difference between getting a 2 with a single event is 16.7%, whereas getting a 2 when we know the outcome is going to be even raises the probability. Almost, let's see, 32. Yeah, it doubles the probability. So since we know the result is even, the sample space gets reduced to what you know. And what we know is that the result will be even. So the probability improves once we know more about the result.